Right now, as you sit, wherever you are reading these words, you are surrounded by what feels like solid reality. The floor beneath you feels firm. The air around you feels real. The walls of the room press outward in every direction and seem to hold the world together. Everything you can touch, everything you can see, everything you can hear or smell or taste, all of it feels substantial, permanent, dense with existence. Everything you just felt is an illusion, not a poetic illusion, not a philosophical one, a physical illusion built by the limitations of human perception and the way matter interacts with itself at scales too small for any unaided eye to resolve. The floor beneath you is not solid. The air around you is not full. The walls of your room are composed almost entirely of emptiness, structured by forces that keep particles at distances so vast relative to their own size that the word solid becomes a convenient fiction rather than an accurate description. But that illusion, the illusion of density of substance of a world packed with matter, extends far beyond the limits of your room. It extends beyond your city, beyond your continent, beyond the planet, beyond the solar system, and beyond the galaxy. At every scale you can examine, the universe turns out to be almost nothing. And at the largest scales, the ones that encompass everything that has ever existed, the universe is so close to absolute nothing that the distinction between something and nothing almost disappears entirely. This is not a metaphor. This is not an exaggeration for dramatic effect. This is the physical reality of the cosmos laid bare by a century of increasingly precise observation and measurement. The universe is overwhelmingly, catastrophically, almost incomprehensibly empty. And understanding why, understanding the mechanisms that produce this emptiness, the history that shaped it, and the extraordinary improbability of anything existing within it at all will change the way you see every star in the night sky, every breath of air you take, and every moment of warmth you have ever experienced on the surface of this planet. The question most people ask about the universe is some version of how big is it, how old is it, how many stars does it contain? These are reasonable questions, and their answers are stunning enough on their own terms. The observable universe spans roughly 93 billion light-years in diameter. It has existed for approximately 13.8 billion years. It contains somewhere between 200 billion and 2 trillion galaxies, each harboring hundreds of billions of stars. Numbers like these are designed to induce awe, and they succeed. Most people who encounter them feel the appropriate vertigo, the sense of scale, collapsing beneath them like a floor giving way. But those questions and those answers are not the right ones to start with. They describe the spectacular exceptions. They count the rare concentrations. They point to the light and ignore the darkness between it. The right question is not how much the universe contains. The right question is how little. And the answer to that question, the true, measured, physically precise answer, is where the real astonishment begins. To understand how empty the universe is, you first have to understand how empty matter itself is, because before you can grasp the emptiness between galaxies or between stars or even between planets, you need to confront the emptiness inside the very substance you are made of. You need to understand that the material world, the apparently solid, dense present world of everyday experience, is itself almost entirely void. Every physical object you have ever touched is composed of atoms. You learned this in school. You know it the way you know that the Earth orbits the Sun, or that DNA carries genetic information as a fact that is true, acknowledged, and then quietly ignored because its implications are too disruptive to sit with comfortably. Atoms are the fundamental units of ordinary matter. They combine to form molecules. Molecules combine to form everything else. Rocks, water, air, living tissue, the chair beneath you, the device you are reading on. So far, this is familiar. Now, consider what an atom actually looks like in terms of scale. The nucleus of an atom, the dense central core containing protons and neutrons, where virtually all of the atom's mass is concentrated, is roughly 1,000,000 times smaller than the atom itself. If you took a hydrogen atom and expanded it until the atom was the size of a professional football stadium, the nucleus sitting at the center would be approximately the size of a marble, a single marble sitting on the 50-yard line of an enormous stadium The electrons, if you could even meaningfully locate them, which quantum mechanics suggests you cannot with precision, would be orbiting somewhere near the outer walls, each one tinier than any dust particle visible to the naked eye. Between the marble and the outer walls, nothing. Empty space, vacuum, absence. This is the internal structure of every atom in your body. Every atom in every rock, every ocean, every mountain, every atmosphere on every planet, orbiting every star, in every galaxy, in the observable universe, shares this architecture. The nucleus is unimaginably small relative to the space the atom occupies. The electrons are smaller still, and the vast interior of every atom is empty. Now, consider what this means for you personally. Your body contains approximately 7 billion atoms. That is, a 7 followed by 27 zeros. An incomprehensible swarm of particles, each one a tiny nucleus surrounded by a vast sphere of emptiness. If you removed all the empty space from every atom in your body, if you could somehow compress all your actual matter together into a solid mass, the result would be a speck of material, roughly the size of a grain of fine sand. A single grain of sand contains everything that is physically, materially you. Your height, your weight, your history, your memories, none of those things are stored in matter. They are patterns in the arrangement of mostly empty atoms. Now extend this to the human species. 7 billion people on Earth, each one compressible to a grain of sand. All of humanity's physical matter assembled together and compressed would fit comfortably inside a sugar cube. Every person who has ever lived, every person alive today, every person who will be born in the foreseeable future, all of it compressed into a cube, smaller than the one you might drop into a cup of coffee. This is the emptiness inside matter. And it is only the beginning. Step outside the atom and consider the scale of objects built from atoms. A single cell, the basic unit of biological life, contains trillions of atoms. But those atoms are not packed tightly. They are arranged in structures, proteins, membranes, organelles with space between them. A cell is less dense than liquid water, which is itself less dense than solid matter. The hierarchy of emptiness continues upward in scale, each level adding more void relative to the matter it contains. A rock which seems solid to every sense you possess is actually a lattice of mineral crystals, atoms bonded to each other in repeating geometric patterns with space between each bond. The rock feels solid because the electromagnetic forces between its atoms are strong enough to resist penetration by the atoms in your hand. You are not touching the rock's matter. You are feeling the repulsive force between two clouds of electrons. The atoms in your fingertips never make contact with the atoms in the rock. They push against each other across a gap. The entire experience of touching anything, the feeling of surface, of resistance, of texture, is mediated by electromagnetic forces operating across empty space. You have never truly touched anything in your life. You have only felt the forces that keep matter from collapsing into itself. This is a strange and uncomfortable fact about physical reality, and it gets stranger as you scale upward. From atoms to molecules to cells to organisms to rocks to mountains to planets, at every level the ratio of matter to empty space remains astonishingly small. A planet which seems dense and substantial from the human perspective is from the atomic perspective almost entirely vacuum. The atoms making up the Earth are so small relative to the planet's total volume that if you could remove all the empty space from every atom in the Earth, our planet would compress to roughly the size of a baseball. A baseball, the entire Earth, all 6 sextillion metric tons of it containing all its oceans and mountains and atmosphere and core, compressed to a baseball. Everything else is empty space, structured by forces. Now leave the Earth. Travel outward through the solar system, and the emptiness compounds at every scale. The distance from the Earth to the Moon is approximately 384,000 kilometers. If you shrank the Earth-Moon system to the size of a basketball and a tennis ball, the distance between them would be roughly 7 meters. 2 balls floating in a room separated by most of the room's width. The solar system is vastly emptier. If you shrank the Sun to the size of a basketball, Neptune would be a small marble sitting approximately 600 meters away. Between those two objects, nothing. Empty space that would take light roughly 4 hours to cross. The nearest star to our Sun, Proxima Centauri, sits approximately 4.25 light-years away, roughly 40 trillion kilometers. Using our basketball-scale model, if the Sun is a basketball sitting in the center of a room, Proxima Centauri is another basketball sitting approximately 4,500 kilometers away. Between them, nothing meaningful. 40 trillion kilometers of vacuum containing on average roughly 1 hydrogen atom per cubic centimeter. The densest clouds between stars might reach a few thousand atoms per cubic centimeter, still a trillion times emptier than the air in your lungs. The fraction of the Milky Way's total volume occupied by the actual physical matter of stars is approximately 1 part in 10 to the 23rd power. That is a decimal point, followed by 22 zeros, and then a 1. Stars, for all their grandeur and luminosity, occupy a fraction of galactic volume, so small it is effectively zero. And the galaxy itself is just one of trillions. The Andromeda Galaxy, our nearest large galactic neighbor, sits approximately 2.5 million light-years away. Between the Milky Way and Andromeda, the density of matter drops to roughly 1 atom per cubic meter. Not per cubic centimeter, per cubic meter. A space the size of your bedroom containing a single solitary hydrogen atom adrift in silence. Between galaxy clusters, the largest gravitationally bound structures in the universe lie cosmic voids. The Boötes void, one of the largest known supervoids, stretches approximately 330 million light-years across and contains fewer than 60 known galaxies in its interior. Compare this to our local region of space, where dozens of galaxies crowd into a region just a few million light-years across. Scientists estimate that cosmic voids occupy between 80 and 90% of the total volume of the observable universe. This means that a randomly selected point in the observable universe has an 80 to 90% chance of being inside a void, far from any galaxy, far from any star, surrounded by nothing but the faintest possible whisper of radiation left over from the Big Bang. The observable universe spans a volume of approximately 4 times 10 to the 80th power cubic meters. The total volume of all stars is approximately 10 to the 51st power cubic meters. Stars occupy roughly 10 to the negative 29th power of the universe's total volume. That fraction has no intuitive analog in human experience. It is the kind of number that, when you stare at it honestly, stops making sense as a quantity and starts functioning only as a symbol for near absolute emptiness. The universe contains 2 trillion galaxies. It contains hundreds of billions of trillions of stars. It contains a number of atoms that cannot be meaningfully spoken aloud. And all of that matter occupies a fraction of the universe's total volume that rounds to zero by any reasonable standard of measurement. This is the universe as it actually is, not the dramatic star-filled luminous spectacle that photographs and films suggest. Those images compress and brighten and select for the interesting parts. The true portrait of the cosmos is a portrait of emptiness, vast, cold, silent, and almost perfectly dark, interrupted at enormous intervals by the briefest sparks of matter clumped together under gravity's insistence. The sparks are real. The light they emit is genuine. The warmth they generate, in at least one celebrated case, has given rise to life and consciousness and the capacity to ask these questions. But the sparks are not the story. The darkness between them is the story. And the darkness goes deeper in temperature, in time, and in implication than most people ever stop to consider. What temperature means when there is almost nothing there. Ask someone how cold space is, and they will give you an answer with complete confidence. Freezing, colder than Antarctica, colder than anything on Earth. They will say it as though the answer is obvious, as though the darkness between the stars must necessarily be frigid in the way a winter night is frigid. Cold air pressing against skin, stealing warmth through direct contact. The kind of cold you can feel in your bones. They are wrong. Not approximately wrong. Not wrong in minor technical details. Wrong in a way that reveals a fundamental misunderstanding about what temperature is, what cold means, and how heat moves through physical reality. The misconception is deeply embedded. Science education reinforces it. Documentaries describe the freezing void between galaxies as though it were a substance with a measurable temperature. Science fiction films show astronauts flash freezing in seconds when exposed to vacuum, as though the cold were actively attacking them. All of this creates an image of space as something cold, in the same way that liquid nitrogen is cold, or a January night in northern Canada is cold. A substance or environment that aggressively pulls heat from anything that enters it. But space is not a substance. The vacuum between stars is not filled with cold stuff. It is filled with almost nothing at all. And nothing cannot be cold in the way a thing can be cold, because cold is not a property of nothing. Cold is a description of how matter behaves. And where there is almost no matter, the concept of temperature becomes strange, strained, and ultimately almost meaningless. Temperature in the physical sense is a measurement of the average kinetic energy of particles. In a gas, it describes how fast molecules are moving. Hot gas contains fast-moving molecules. Cold gas contains slower ones. When those molecules collide with your skin billions of times per second in normal air, they transfer energy. Fast molecules transfer more energy than slow ones. Your nervous system interprets rapid energy transfer as heat. Slow energy transfer registers as cold. This physics requires matter. It requires particles. It requires collisions. Take away the particles and the physics of temperature changes completely. In a perfect vacuum, temperature in this conventional sense does not apply. There are no particles to measure. There are no molecules to collide with your skin. The concept dissolves into abstraction. In the near vacuum of deep space, the particle density is so low that meaningful temperature measurement becomes nearly impossible through conventional means. A thermometer placed in deep space would not read the temperature of space. It would read its own temperature. The thermometer becomes the subject of its own measurement. It tells you about itself, not about the void surrounding it. This reveals the first key truth about thermal conditions in space. Temperature is a property of objects in space, not of space itself. The void does not have a temperature in the way a gas has a temperature. What it has is a radiative environment, a set of electromagnetic conditions that determine how objects within it gain and lose thermal energy through the only mechanism that works in vacuum. That mechanism is radiation. Heat transfers through three mechanisms: conduction, convection, and radiation. Conduction requires physical contact, molecules in one object vibrating against molecules in another, passing kinetic energy directly from warm to cool. Convection requires a fluid medium, the circulation of air or water or any other flowing substance carrying heat from one place to another through bulk movement. Both of these mechanisms require matter. Neither works in vacuum. Radiation requires nothing. Every object with a temperature above absolute zero emits electromagnetic radiation photons carrying energy outward in all directions at the speed of light. Your body emits infrared radiation right now, streaming outward invisibly in every direction. The walls of your room emit infrared radiation back. The sun emits radiation across a vast electromagnetic spectrum. This radiation crosses empty space without any medium to carry it. In space, radiation is the only game. It is the only mechanism through which any object can gain or lose thermal energy. And this transforms the thermal experience of any object in space into something genuinely alien. Consider an astronaut performing a spacewalk in low Earth orbit. On the sunlit side of the suit, solar radiation pours in at approximately 1360 watts per square meter, equivalent to running a powerful space heater against every square meter of illuminated surface. Without active cooling, the sunlit side of the suit heats well above 100 degrees Celsius. On the shadowed side of that same astronaut, the side facing away from the sun, there is no incoming solar radiation. The temperature can drop to negative 100 degrees Celsius or lower. One astronaut, two sides of a body, a temperature difference of 200 degrees or more across a distance you could span with your outstretched arms. Not because space is different temperatures in those directions. Space has no temperature in those directions. The astronaut is simply caught between a powerful radiation source on one side and the absence of any radiation source on the other. This is what makes the thermal environment of space so alien and so dangerous. On Earth, Air acts as a thermal buffer. Move from sunlight into shade, and the air temperature barely changes, perhaps a degree or two at most, because convection continuously mixes the atmosphere. In space, there is no buffer, no mixing, no smoothing. Radiation creates savage thermal gradients across distances as small as the width of a human body. The Moon provides the most dramatic demonstration of this principle. The lunar surface has no atmosphere. When the sun shines on the lunar equator during the roughly 2-week lunar day, the surface heats to approximately 127 degrees Celsius. When that same surface rotates into the 2-week lunar night, it cools to approximately negative 173 degrees Celsius. A swing of 300 degrees on the same patch of ground, driven entirely by the presence or absence of sunlight, with no atmospheric buffer to moderate the transition. Earth's surface, protected by its atmosphere, experiences temperature swings of perhaps 50 to 60 degrees between the hottest days and coldest nights in even the most extreme desert environments. The Moon experiences swings 5 times more violent and with no gradual transition between extremes. This is why spacecraft engineers do not think about the temperature of space as a design parameter. They think about thermal balance, the equilibrium between energy absorbed and energy emitted by each component. The International Space Station uses enormous radiator panels spanning roughly 2,500 square feet facing away from the sun to dump excess heat generated by the station's electrical systems, computers, and 6 human crew members. Without these radiators, the station would overheat from its own internal heat generation alone. Simultaneously, components sitting in shadow require electric heaters to prevent them from freezing. The station exists in constant thermal tension, simultaneously fighting overheating and freezing, managed by systems that continuously monitor hundreds of temperature sensors as the station cycles in and out of sunlight 16 times per day. Strip away the engineering complexity and the core physical reality emerges. Clearly, the thermal environment of space is not defined by some ambient temperature surrounding objects. It is defined entirely by the radiative balance of each individual object, how much radiation it absorbs from whatever sources happen to be shining on it, and how much it emits based on its own temperature. Far from any star in the interstellar void or in the vast reaches of intergalactic space, the only radiation available to warm an object is the faintest possible background glow, not starlight, which falls off with the square of distance and becomes negligible at interstellar distances. Something older, colder, and more fundamental. The oldest light in the universe, the last remnant of the primordial fire that created everything. This is the cosmic microwave background, the thermal floor of the universe, and it sets the baseline temperature for everything that exists. Understanding it requires going back to the absolute beginning. The moment the universe was born in a state of heat so extreme, it makes the interior of the most massive stars look cool by comparison. How a universe born in fire became a universe, defined by darkness. The universe did not begin cold. This cannot be overstated. The conditions that existed in the first fractions of a second after the Big Bang were so far from cold, so utterly removed from anything resembling the temperatures we associate with space, that describing them requires abandoning every intuitive scale of reference. In the first instant after the Big Bang, the entire observable universe, everything you can see through the most powerful telescope ever built, every galaxy and cluster and void and filament spanning 93 billion light-years in every direction, was compressed into a volume smaller than a single proton. The temperature in that primordial instant exceeded 10 to the 32nd degrees Kelvin. That number, a 1, followed by 32 zeros, has no meaningful comparison. It is hotter than the core of any star by a factor of billions of billions. It is a temperature so extreme that the known laws of physics break down completely in attempting to describe it. Whatever existed at that moment was not matter in any form. We recognize not energy in any form we can describe, but some primordial state in which the distinction between matter and energy and space-time itself had not yet become meaningful. The universe was born in a state of thermal violence that exceeds every scale of comparison human minds have ever developed, and it has been cooling ever since. The cooling began immediately. As space expanded, the temperature dropped. In the first second after the Big Bang, the universe cooled from its initial inconceivable heat to approximately 10 billion degrees. That sounds like catastrophic cooling, and it was. But 10 billion degrees is still hotter than the core of the most massive stars in existence today. The universe at 1 second old was a blazing plasma, a dense, uniform, opaque soup of protons, neutrons, electrons, photons, and neutrinos, all colliding continuously with energies that would vaporize any structure that exists in the modern cosmos. At these temperatures, matter and radiation were locked together. Photons could not travel more than a microscopic distance before colliding with a charged particle and scattering in a random direction. The universe was opaque. Light existed everywhere, but could go nowhere. Every direction was a wall of blazing, impenetrable fog. Between 1 second and 3 minutes after the Big Bang, the temperature fell to roughly 1 billion degrees. At these temperatures, nuclear fusion became possible. Protons and neutrons began sticking together, forming the lightest atomic nuclei. This process, called Big Bang nucleosynthesis, lasted only about 17 minutes before the temperature fell too low for nuclear fusion to continue. The window opened and closed faster than most humans live through a single afternoon. The ratio of hydrogen to helium was fixed at approximately 75% hydrogen and 25% helium by mass, to a ratio confirmed to extraordinary precision by observations of the oldest stars, providing powerful evidence that our understanding of the Big Bang's first minutes is correct. For the next roughly 38,000,000 years, the universe remained hot enough to keep all matter in plasma form. Free electrons roamed everywhere, continuously scattering photons and keeping the universe opaque. Despite the unimaginable progress from the first second to thousands of years later, the universe was still effectively a single glowing fog-hot, dense uniform and impenetrable to light. Then approximately 38,000,000 years after the Big Bang, the universe crossed a critical threshold. The temperature dropped below roughly 30,000 Kelvin. Electrons, which had until this moment been too energetic to remain bound to atomic nuclei, finally slowed enough to be captured. Protons grabbed electrons and became neutral hydrogen atoms. For the first time in cosmic history, matter was electrically neutral. Neutral atoms do not scatter photons the way free electrons do. When the electrons disappeared into atoms, the universe became transparent, essentially instantaneously on cosmological timescales. The photons that had been trapped bouncing off electrons in every direction, unable to travel more than a short distance before scattering again, were suddenly liberated. They streamed outward in straight lines for the first time in the universe's history, carrying information about the conditions at the moment of their release. Those photons have been traveling ever since. Nearly 13.8 billion years of continuous, uninterrupted travel across an expanding universe. They fill every cubic centimeter of the observable cosmos, arriving at Earth from every direction in the sky, carrying the oldest light that the universe will ever produce. But they do not arrive as they departed. When those photons were released at the moment of recombination, they were visible light photons, corresponding to radiation from a surface at 3000 Kelvin. If you could have been present at that moment, the entire sky in every direction would have glowed a deep, uniform dark red. No stars, no galaxies, no structure of any kind, just the uniform warm glow of a universe cooling from its fiery beginning. Since that moment, the universe has expanded by a factor of approximately 1100. Space itself stretched, and every photon traveling through it stretched along with space. Longer wavelengths mean lower energy, and lower energy means lower effective temperature. The visible light of recombination has been stretched so dramatically over 13.8 billion years that it now exists as microwave radiation waves, roughly a millimeter long, completely invisible to human eyes. The temperature of this radiation when measured today is 2.725 Kelvin. The entire sky still glows just as it did at recombination, but the glow has been shifted so far down the electromagnetic spectrum that it is invisible without instruments specifically built to detect it. This is the cosmic microwave background, the thermal fossil of recombination, the oldest light in the universe, the echo of the moment the cosmos first became transparent. The discovery of this radiation is one of the great scientific accidents in history. In 1964, Arno Penzias and Robert Wilson, radio astronomers at Bell Telephone Laboratories in New Jersey, were attempting to use a large horn-shaped antenna for satellite communication work. They were meticulous experimenters who wanted to minimize noise in their system. They accounted for radio interference from New York City. They pointed the antenna away from known radio sources. They calibrated their equipment carefully. They even climbed inside the antenna and scraped out the droppings of pigeons that had been nesting in the horn, genuinely suspecting that bird excrement might be generating thermal noise in their signal. Nothing worked. A persistent faint hiss remained no matter what they did. It came from every direction equally. It did not change with the time of day, the season, or where they pointed the antenna. The signal was perfectly uniform, perfectly constant, and corresponded to a thermal source at approximately 3.5 Kelvin, just a few degrees above absolute zero. Penzias and Wilson were puzzled. They spent months searching for an explanation. The connection between their noise and the origin of the universe came from a group of theoretical physicists at Princeton University just 40 miles away who had independently predicted that the Big Bang should have left behind exactly this kind of faint uniform radiation. The persistent hiss was not instrument error. It was not pigeon droppings. It was not local radio interference. It was the oldest light in the universe arriving at a satellite antenna in New Jersey after a journey of nearly 13.8 billion years. Penzias and Wilson received the Nobel Prize in Physics in 1978. The decades following this discovery transformed the cosmic microwave background from an accidental detection into the most precisely studied and scientifically productive phenomenon in all of cosmology. 3 major satellite missions, NASA's COBE in 1989, WMAP in 2001, and the European Space Agency's Planck in 2009, mapped the CMB across the entire sky with steadily increasing precision. COBE made 2 foundational discoveries. First, it measured the spectrum of the CMB and found it to be the most perfect blackbody spectrum ever observed in nature, confirming the Big Bang theory with extraordinary precision. The temperature was pinned to 2.725 Kelvin. Second, COBE detected tiny temperature fluctuations in the CMB variations of roughly 1 part in 1,000,000 across the sky. These variations were the fingerprints of density fluctuations in the early universe, the seeds from which all cosmic structure would eventually grow. WMAP refined the map with 35 times the angular resolution of COBE, establishing the age of the universe at 13.77 billion years, confirming that ordinary matter constitutes only about 4.6% of the total energy content of the cosmos, and showing that dark matter and dark energy make up the remaining 95%. Planck pushed further, still mapping the CMB at 9 different frequency bands and confirming the WMAP results while adding new precision. It measured the universe's age at 13.798 billion years and revealed subtle polarization patterns in the CMB that carry information about the earliest moments of cosmic history. All of this science, everything we know about the large-scale properties of the universe, about its age and composition and geometry, flows from careful measurement of a faint microwave hiss filling the sky at 2.725 Kelvin. The oldest light in the universe, stretched and cooled beyond visibility, carries the most detailed record of cosmic history available to observation. But the cosmic microwave background is not static. It is cooling. The universe continues to expand. As it does, the microwave photons continue to stretch their wavelengths, growing longer, their energies declining, their effective temperature falling. The 2.725 Kelvin we measure today was 5 Kelvin when the universe was half its current size. When the universe doubles in size, the CMB will be approximately 1.4 Kelvin. When it grows 10 times larger, the background will hover around 0.3 Kelvin. The afterglow of creation is fading, slowly, imperceptibly by human standards, but inexorably on cosmological timescales. The fire that created everything is cooling toward a darkness that it will approach asymptotically but never quite reach, because the laws of thermodynamics forbid any physical process from achieving absolute zero through a finite sequence of steps. Today, 2.725 Kelvin is the floor, the cosmic minimum, the temperature that any object in deep space far from any star or galaxy will eventually cool to as it radiates its own heat into the void and receives back only the faint contribution of the cosmic microwave background. This floor, barely above absolute zero, colder than liquid helium, 68 times colder than the coldest temperature ever recorded in Earth's atmosphere, is the default thermal condition of the universe, not a special case, not an extreme outlier. The default. This is the cold at the heart of everything. And understanding its origin is only the beginning of understanding what it means. Stars, their heat, and the overwhelming darkness they cannot touch. Stars are miraculous. There is no more precise or honest way to describe them. In a universe that defaults to temperatures barely above absolute zero, a star represents a sustained act of thermal defiance, so extreme that it seems almost philosophically improbable. Our sun burns at 5500 degrees Celsius at its surface and 15 million degrees at its core. These temperatures exist on a completely different scale from the 2.725 Kelvin surrounding them, separated from the cosmic baseline by factors of millions maintained by the nuclear reactions at the star's heart. Every star you can see with the naked eye on a clear night is performing this same act, converting matter into energy through nuclear fusion, maintaining a ball of plasma against the dual pressures of its own gravity, pulling inward, and the radiation pressure of its nuclear reactions, pushing outward. The balance between these forces defines stellar physics and determines everything about how a star lives and how it dies. Our sun is by stellar standards average in almost every respect. Its mass falls near the middle of the stellar mass range. Its surface temperature is typical for a yellow dwarf star. Those massive stars at the extreme upper end, the blue supergiants and Wolf-Rayet stars, burn at temperatures that dwarf the sun's modest contribution. Rigel, the brilliant blue-white star at the foot of Orion, blazes at surface temperatures exceeding 11,000 degrees Celsius, roughly twice the sun's surface temperature. Its luminosity is approximately 12,000 times greater than the sun's. But these luminous giants pay for their extravagance with brevity. The most massive stars burn through their hydrogen fuel in as little as 1 to 3 million years before dying in cataclysmic supernova explosions. Compare this to the sun's expected 10 billion year lifespan, or to the trillion-year lifespans of the smallest red dwarf stars. At the opposite extreme, red dwarf stars, comprising roughly 70% of all stars in the Milky Way, burn so dimly that not a single red dwarf is visible to the naked eye from Earth, despite being far more numerous than any other stellar variety. Their surface temperatures hover around 3000 degrees Celsius, but their fuel efficiency is extraordinary. The smallest red dwarfs will burn for 10 to 15 trillion years, 1,000 times the current age of the universe. Not one red dwarf that has ever ignited is dead. Not one has run out of fuel. They are all still burning, every single one quietly and patiently in the darkness. The thermal output of stars is real and substantial on a cosmic energy budget, but it is confined to space at distances where it matters. And that confinement is the crucial fact. Each star heats a small sphere of space around itself. The habitable zone, the narrow orbital ring where temperatures permit liquid water on a rocky planet, spans roughly 70 million kilometers in width for a sun-like star. Against the backdrop of interstellar distances measured in light years, tens of trillions of kilometers, 70 million kilometers, is not just small, it is essentially invisible. The distance from the sun to the nearest star is approximately 40 trillion kilometers. The habitable zone around our sun is 70 million kilometers wide. The habitable zone occupies less than 2/10,000ths of 1% of the interstellar gulf. Every star maintains a thermal sphere around itself, and every thermal sphere is infinitesimally small relative to the vast cold distances separating stars. Between those thermal spheres, between one star's zone of meaningful warmth and the next, lies cold space at or near the cosmic microwave background temperature. Cold that has persisted since before any star existed. Cold that will persist long after the last star has gone dark. Accretion disks around black holes represent even more extreme thermal environments. The inner regions of accretion disks around stellar mass black holes can reach temperatures of tens of millions of degrees. Around supermassive black holes with masses millions or billions of times the sun's accretion disk temperatures can reach hundreds of millions to over 1 billion degrees Celsius. These are among the highest sustained temperatures in the modern universe. But the volume these extreme temperatures occupy is microscopic. An accretion disk around a stellar mass black hole might span a few thousand kilometers in its inner regions. Their thermal contribution to the universe's total energy budget is significant, but localized hotspots in a cold cosmos, more intense than stars, but occupying even less volume. The most dramatic thermal events in the modern universe are supernovae, when a star more than 8 to 10 times the sun's mass exhausts its nuclear fuel. Its iron core collapses in less than a second. The temperature at the collapsing core reaches approximately 100 billion degrees hotter than any stable stellar interior, hotter than any accretion disk, hotter than the universe has been at any point since the first second after the Big Bang. In that brief, violent instant, lasting perhaps 10 to 20 seconds, a dying star briefly recreates conditions that existed when the cosmos was less than 1 second old. The energy released can rival the luminous output of the entire visible universe. The electromagnetic display can outshine the combined light of every star in the host galaxy for weeks. And then it fades. The shockwave expands and cools. The expanding supernova remnant gradually merges with the surrounding interstellar medium, its energy dissipating into the cold void. The thermal violence is spectacular, but transient, a single candle burning briefly in a vast dark room before the darkness reclaims it entirely. Assembling all these hot objects together, all the stars, all the accretion disks, all the supernovae, all the nebulae and stellar nurseries and ionized gas clouds, and measuring their total thermal contribution against the total volume of the observable universe produces a number that is challenging to communicate without loss. The fraction of the universe's total volume occupied by matter at temperatures above the freezing point of water is approximately 10 to the negative 24th power. That is a decimal point followed by 23 zeros and then a 1. Both numbers are for practical purposes zero. The universe contains an enormous number of hot objects. It contains hundreds of billions of trillions of stars. It contains millions of actively accreting black holes. And all of these objects together, combined, summed, assembled into the most generous possible thermal accounting, occupy a fraction of the universe's total volume that is indistinguishable from zero when measured honestly. The hot objects are real. The light they emit is real. The warmth they provide is real. But they are not the universe. They are what the universe does in isolated pockets, under extraordinary circumstances for limited periods of time. The universe itself, the vast majority of its volume, essentially all of its extent, sits at or near 2.725 Kelvin, cold in a way that has no adequate analog in daily life. Cold is not a property of space, but it is overwhelmingly and definitively the condition of the cosmos. How the universe organizes its nothing. The universe is not randomly empty. Its emptiness has structure of vast three-dimensional architecture of filaments and walls and voids that represents the largest patterns in nature, shaped by gravity acting over billions of years on the density fluctuations seeded in the first moments after the Big Bang. This structure, called the cosmic web, is the largest thing in the universe. It is the framework within which every galaxy, every star, every planet, and every living thing that exists is embedded. And understanding its most prominent feature, the cosmic voids that dominate its volume, means confronting the emptiness of the universe, not as an abstract number, but as a physical reality with geographic extent, thermal properties, and a history stretching back to the earliest moments of cosmic time. The cosmic web emerged from tiny density fluctuations in the early universe. At the moment of recombination, the distribution of matter across the observable universe was extraordinarily uniform. The temperature fluctuations measured in the CMB at the level of 1 part in 1000000 reflect density fluctuations of similar magnitude. Some regions of the early universe were very slightly denser than average. Others were very slightly less dense. But gravity is patient and persistent. Over hundreds of millions of years, slightly denser regions attracted surrounding matter. Their gravity grew stronger as they became denser, attracting still more matter in a runaway process. Meanwhile, slightly underdense regions lost matter to their denser neighbors, becoming emptier over time. The small initial differences amplified over cosmic time into the dramatic contrasts we see today. Dense galaxy clusters at the intersections of luminous filaments separated by vast, nearly empty voids. The large-scale structure of the universe mapped by surveys like the Sloan Digital Sky Survey that measured the positions and redshifts of millions of galaxies resembles foam when visualized. Thin, luminous walls and filaments surround enormous dark voids. The bright parts where galaxies and galaxy clusters trace out the scaffolding of the web look like the surfaces and edges of soap bubbles. The dark parts, the interiors of the voids, are the empty spaces inside the bubbles. In this foam, the bubbles are the dominant feature. A typical cosmic void spans 100 to 300 million light-years across. The largest known voids exceed 1 billion light-years in diameter. The Boötes void, discovered in 1981, when astronomers noticed an inexplicable absence of galaxies in that region of the sky, stretches approximately 330 million light-years across and contains fewer than 60 known galaxies within its boundaries, far fewer than would be expected, given its volume. If Earth were located at the center of the Boötes void, the nearest galaxies would be so distant that they would have been invisible through telescopes available until relatively recently. The night sky beyond the stars of our own galaxy would have appeared almost perfectly dark. The cosmic web would have been invisible from such a location, not because it does not exist, but because none of its luminous markers would be close enough to detect. Inside these voids, the thermal environment approaches its purest possible state. No galaxies means no stars burning in meaningful numbers. No stars means no local radiation sources heating the surrounding space above the cosmic microwave background. No heating means equilibrium at 2.725 Kelvin, the universal floor essentially undisturbed. The void temperatures are stable on timescales that dwarf geological epochs. The Boötes void has been thermally at or near the CMB temperature since long before the first stars ignited in our galaxy. It will remain at that temperature until the universe's expansion cools the CMB further century by century, eon by eon, reducing an already almost inconceivably cold baseline toward a slightly colder one. No dramatic events disturb void temperatures. No supernovae light up the interior. No active galactic nuclei pour radiation into the darkness. The void is thermally quiet in a way that no place on Earth and no place near any star can match. Even within the luminous filaments, the regions of the cosmic web that contain galaxies, the thermal situation is dominated by cold in terms of volume. Galaxies themselves are mostly empty space at the scales of interstellar distances. Walk a straight line through the Milky Way in a random direction, and you would spend the overwhelming majority of your journey in cold interstellar vacuum, far from any star, bathed in nothing but the CMB and the attenuated light of distant stellar population. The interstellar medium exists in several distinct phases with very different properties. The hot ionized medium heated by supernova remnants and young massive stars reaches temperatures of 1,000,000 Kelvin or more, but is so diffuse with densities of only a few thousandths of an atom per cubic centimeter that its thermal energy content per unit volume is negligible. The cold neutral medium hovers at 100 Kelvin. Dense molecular clouds where star formation occurs can be as cold as 10 Kelvin, barely warmer than the CMB. Star formation, the process that creates the universe's hottest objects, begins in its coldest places. The seeds of stellar fire germinate in the deepest cold at temperatures a few times the CMB floor. This is not a paradox, but a consequence of physics. Only where gas is cold enough to resist the thermal pressure that would otherwise prevent gravitational collapse can a cloud of gas condense into a stellar embryo. Warmth prevents star formation. Cold enables it. The intergalactic medium, the gas between galaxies, presents perhaps the most interesting thermal puzzle in the cosmic web. A significant fraction of all ordinary matter in the universe perhaps 40 to 50% resides in the warm-hot intergalactic medium, or WIM. This gas exists in filaments and sheets between galaxy clusters, heated to temperatures of 100,000 to 10 million Kelvin by gravitational shocks. 10 million Kelvin sounds hot, but this is a gas of extraordinary thinness, densities of perhaps a few atoms per cubic meter. The thermal energy content of such a gas per unit volume is almost nothing. Stand inside a cubic meter of WIM and you would feel nothing. Not because the particles are moving slowly, they are moving fast, but because there are so few of them that their collective energy contribution is negligible. This distinction between temperature and thermal energy density is essential for understanding the cosmos. Honestly, a gas can have extremely high temperature and extremely low thermal energy density simultaneously, as long as its density is sufficiently low. The WIM is the extreme example technically among the hottest gas in the universe, but thermally irrelevant for any practical purpose because it is so dilute. The cosmic web, in its full three-dimensional extent, is the most complete expression of the universe's thermal reality. It concentrates matter into the thin, luminous structures of filaments and walls. It produces galaxy clusters at their intersections, and it leaves the vast interiors of voids essentially untouched, cold, dark, and thermally static, across spans of hundreds of millions of light years. The ratio of void to structure in the cosmic web, roughly 80 to 90% void by volume, means that the thermal portrait of the universe is determined overwhelmingly by what happens in the voids, and in the voids what happens thermally is almost nothing. The CMB provides a minimum energy input. Objects cool toward 2.725 Kelvin. The darkness is undisturbed by any local source of warmth. The galaxies and clusters and filaments are real and important and spectacularly interesting, but they are inscribed on a background of cold emptiness, so vast and so dominant that the structures themselves are like fine writing on an enormous dark page, meaningful and intricate to anyone looking closely but invisible from a distance, against the overwhelming blank darkness of the sheet, where the universe is going and what waits at the end. The universe's thermal history has been a story of cooling from unimaginable heat toward the near absolute cold that defines the present. But the story is not finished. The cooling continues. The expansion continues. The future of the universe, written in the physics of thermodynamics and the mathematics of expansion, is a future of increasing cold, deepening darkness, and ultimately a silence so complete that the word silence seems inadequate to describe it. Understanding the future requires understanding the present trajectory. The universe today is expanding, and as observations since the late 1990s have confirmed that expansion is accelerating. Dark energy, the mysterious component making up roughly 68% of the universe's total energy content, is driving the cosmic expansion to speed up over time. As the expansion accelerates, galaxies outside our local gravitational neighborhood are receding from us at increasing rates. Eventually, galaxies currently visible to us will be receding faster than light, crossing a cosmological horizon beyond which we can never observe or communicate. The observable universe will shrink, not in physical size but in the volume accessible to any observer. The galaxies beyond the accelerating horizon will disappear, not destroyed, but rendered forever invisible by the expansion of space carrying them beyond the reach of any signal. The universe will become lonelier. In a very literal sense, the number of galaxies visible from our location will decline over time as more and more of them accelerate beyond the horizon. Stars will burn for a long time. The current epoch, cosmologists call it the stelliferous era, has another roughly 100 trillion years to run. During this time, stars will continue forming from gas clouds in galaxies, burning through their nuclear fuel and dying, while new generations form from the enriched gas left behind by their predecessors. The rate of star formation is declining. It peaked roughly 10 billion years ago and has been falling since, but it has not yet reached zero and will not for a very long time. As the stelliferous era continues, the stellar population will change character. Massive stars which burn bright and die young will become rarer as the gas available for their formation is consumed and not replenished. The stellar population will shift progressively toward lower mass stars. then to the smallest and most fuel-efficient red dwarfs, which will dominate the stellar census for the bulk of the stelliferous era's remaining duration. When the last red dwarf finally exhausts its hydrogen, perhaps 10 to 15 trillion years from now, there will be no more nuclear fusion anywhere in the universe. Not because the rules of physics have changed, but because the raw material has been used up. The stars will go dark, one by one, over a period vastly longer than the current age of the universe. The last stellar light will simply fade quietly and without ceremony, leaving behind a cosmos of cooling remnants. The remnants left behind will be white dwarfs, the compressed cores of stars like our Sun, the size of Earth, but with the mass of a stellar interior. White dwarfs produce no nuclear energy. They simply radiate away the heat they contain, cooling over time from luminous white to yellow to orange to red to infrared. Over time, scales measured in quadrillions of years, they will fade to temperatures indistinguishable from the cosmic background. Each cooling white dwarf is a tiny reenactment of the universe's own thermal history. Born hot, fading, slowly approaching but never quite reaching absolute cold. Black holes will dominate the mass budget of the very far future. They do not cool in the same way. Through the quantum mechanical process described by Stephen Hawking in 1974, they emit very slowly through what is called Hawking radiation, a quantum effect in which virtual particle pairs near the event horizon separate, with one particle falling in and the other escaping. A stellar mass black hole takes approximately 10 to the 67th power years to evaporate through Hawking radiation. A supermassive black hole with a mass of billions of solar masses takes roughly 10 to the 100th power years. These numbers are so large, they effectively resist comparison. The age of the universe is 13.8 billion years, roughly 10 to the 10th power. A supermassive black hole requires 10 to the 100th power years to evaporate 90 orders of magnitude longer than the current age of the universe. When the final black hole evaporates in a burst of Hawking radiation, releasing its remaining mass as photons, the universe will contain nothing but radiation and a scattering of subatomic particles drifting apart in an expanding void at temperatures so close to absolute zero that the distinction becomes meaningless. The endpoint that physics projects for the universe's thermal future is called the heat death. Despite the word heat, it is not a hot end. It is the coldest possible end, a state of maximum entropy in which all energy is distributed perfectly uniformly across the universe, with no gradients, no concentrations, no temperature differences of any kind. Without temperature differences, no work can be done, no processes can occur, no information can be processed. Nothing happens, and nothing can happen because thermodynamics requires a difference in temperature to drive any physical process, and there are none. The heat death is not a burning end, it is a frozen end. A universe in thermal equilibrium at a temperature so close to absolute zero that the difference is physically meaningless, expanded to an extent so vast that even the CMB photons have been stretched beyond any conceivable measurement, darker than anything that currently exists or has ever existed, silent in a way that has no precedent. The universe will die not with fire, but with cold. Against this backdrop, the present moment takes on an extraordinary quality. We exist during the stelliferous era, the window when stars burn, when warmth is available, when temperature differences drive the chemistry and physics of complexity. That window is open now, and it will be open for a long time. By human standards, another 100 trillion years is an almost inconceivable future. But against the full timeline of the universe, stretching from 10 to the 100th power years and beyond, the stelliferous era is a brief flash. If the universe's full future were represented as a single year, the entire era of starlight would occupy the first few milliseconds of January 1st. Everything after that, every year remaining in the calendar, every month, every week, every day, every second would pass in total darkness at temperatures approaching absolute zero. The stars are temporary. The warmth they provide is temporary. The conditions they create, the narrow thermal windows around their surfaces where liquid water can pool and complex chemistry can operate, are temporary. We exist during the brief cosmic moment when these conditions are available. What it means to be warm in a universe that is mostly cold. Hold all of this together in your mind for a moment. The universe began in heat so extreme that the word extreme loses meaning. It has been cooling for 13.8 billion years. The expansion of space has stretched the primordial fire into a faint microwave whisper at 2.725 Kelvin, barely above the absolute coldest condition that physics permits. Stars burn as local exception, furious and brilliant, but occupying a fraction of cosmic volume so small that expressing it in ordinary language is impossible. Cosmic voids spanning hundreds of millions of light years sit at the universal baseline temperature, undisturbed for durations that make geological epochs seem brief. And the future stretches out toward a heat death of maximum cold, trillions of years of increasing darkness and decreasing temperature, ending in a stillness so absolute that no physical process can disturb it. Now look around you. The room you are in right now maintains a temperature somewhere between 15 and 25 degrees Celsius, approximately 288 to 298 Kelvin. That temperature is sustained by the sun's output, mediated by Earth's atmosphere, buffered by the oceans, regulated by the carbon cycle, and maintained locally by whatever heating or cooling system you have access to. It is a temperature approximately 100 times higher than the cosmic baseline, a temperature that keeps water liquid, a temperature that allows proteins to maintain their three-dimensional shapes, a temperature at which chemical reactions proceed at rates compatible with biological function, fast enough to sustain metabolism, slow enough to allow molecular machines to operate without random thermal disruption. That temperature, so ordinary, so taken for granted, so unremarkable in the context of everyday human experience, is one of the most cosmically unusual conditions in the observable universe. Think about what is required to produce it. Start with the obvious: a star. Not just any star. A star of the right mass to burn stably for billions of years without sterilizing its inner planets with ultraviolet radiation or failing to provide sufficient energy for complex chemistry. The sun has burned at a luminosity within roughly 30% of its current value for 4.5 billion years, long enough for evolution to produce everything from the first self-replicating molecules to the neural complexity required for abstract thought. Earth must orbit at the right distance. The habitable zone spans a narrow ring between roughly 0.95 and 1.7 astronomical units from our Sun. Earth orbits at 1 astronomical units, threading the needle with a precision that looks from a cosmic vantage point almost calculated. Earth must have an atmosphere of the right composition. Without the greenhouse effect, Earth's average surface temperature would be approximately -18 degrees Celsius, well below the global freezing point. The greenhouse effect raises the actual average to approximately +15 degrees Celsius, a swing of 33 degrees that makes the difference between a frozen, sterile world and a living one. Earth must have a magnetic field strong enough to deflect the solar wind, the stream of charged particles from the sun that would otherwise strip away the atmosphere over geological time, as apparently happened to Mars. Earth's magnetic field is generated by convection currents in its liquid iron outer core, driven by the heat of radioactive decay and the secular cooling of the planet. Earth must have water in the right quantity. Too little and the planet dries out, unable to support the carbon cycle or the ocean heat sink that moderates climate. Too much, and a global ocean covers everything, preventing the geological activity needed to cycle carbon between the atmosphere and the crust. Earth must have a large moon to stabilize its axial tilt. Without the moon's gravitational influence, Earth's axial tilt would vary chaotically, producing climate swings so extreme that the stability required for complex biological evolution might be impossible. Layer these requirements one on top of another, and a picture emerges of how many conditions must align simultaneously for a planet to maintain the extraordinary thermal conditions that support life. Each requirement narrows the field of candidates. Each additional constraint makes the final count smaller. The universe contains roughly 2 trillion galaxies. Each harbors hundreds of billions of stars. Each star has some probability of hosting rocky planets in its habitable zone. But the probability of any such planet actually maintaining life-friendly conditions over the billions of years required for complex life to evolve given all the additional requirements beyond mere orbital distance, remains deeply uncertain. The James Webb Space Telescope is beginning to probe exoplanet atmospheres in the habitable zones of nearby stars, searching for chemical signatures that might indicate conditions compatible with life. In the coming decades, this search will expand. We may find evidence of habitable conditions elsewhere. We may find signatures of biology, or we may find nothing, a silence that would carry its own profound information about the rarity of the conditions we experience here. But regardless of what those searches reveal, one fact is already established beyond doubt. The conditions on Earth's surface, the temperature, the chemistry, the liquid water, the atmospheric composition are extraordinarily rare when measured against the thermal conditions that characterize the overwhelming majority of the observable universe. The terrifying truth about the universe's cold is not the number. It is not 2.725 Kelvin, though that number is extraordinary enough. It is not the fraction of cosmic volume at stellar temperatures, though that fraction 10 to the negative 29th power should stop anyone in their tracks. The terrifying truth is the proportion, the ratio of cold to warm, the overwhelming total permanent dominance of cold over warmth in the physical universe. Most of the universe is cold, not cold in a temporary way pending some future warming, not cold the way winter is cold, which ends when spring arrives, cold in the permanent structural way because the initial heat was deposited once at the Big Bang and it has been diluting ever since, and no process in nature replenishes it at cosmic scales. Stars convert matter to energy and radiate it into the void, accelerating the dissipation of usable energy rather than creating new heat for the cosmos. Every star that burns is hastening the universe toward its final equilibrium of perfect, absolute permanent cold. The warmth we inhabit is not the default. It is not the expected condition. It is not what the universe tends toward or rewards with persistence. The warmth is what happens briefly and locally when gravity gathers enough matter in one place to ignite nuclear fire, and when the geometry of a planet's orbit and the chemistry of its atmosphere and the stability of its geology and the presence of liquid water all align simultaneously to create and sustain conditions compatible with the extraordinary accident of biology. Every one of those alignments could have failed. Most of them do fail. In most of the places across the universe where the opportunity arises, the universe is indifferent to warmth. It neither encourages it nor seeks to destroy it. It simply tends over time toward maximum entropy, and warmth is a departure from that tendency that requires specific physical conditions to maintain and ends when those conditions cease. None of this is cause for despair. The warmth is here. The conditions that sustain it persist for now, with every reasonable expectation of continuing for billions of years before the sun's evolution renders the Earth uninhabitable. Billions of years is a duration that no human experience can meaningfully encompass. It is time enough for everything we might ever become, everything our species or its descendants might ever do or know or build or understand. But knowing the universe for what it is, knowing the cold that surrounds the warmth, knowing the brevity of the stellar era against the deep time of the universe's cooling future, knowing the rarity of conditions like those on Earth against the overwhelming thermal emptiness of the cosmos changes the meaning of the warmth. It makes it something that demands acknowledgement rather than being taken for granted, not with fear, not with grief, but with the clear-eyed recognition of what we have and what it cost the universe to produce it. Every sunrise is an event of cosmic improbability, not because physics demanded it, but because the chain of physical contingencies stretching from the Big Bang to this morning included every necessary step and excluded no fatal failure. Every ocean that remains liquid, every breath of warm air, every biological process that proceeds at a temperature compatible with the chemistry of life, all of it exists against a backdrop where none of it had to exist, where most of the universe's volume contains nothing like it, and where the future will be overwhelmingly defined not by warmth, but by its absence. Look up on a clear night. See the stars. Know what they are, each one a furnace tiny against the distances that separate them, burning through its fuel supply on a timeline fixed by its mass, creating a small warm zone around itself in which the improbable might happen. Planets, chemistry, biology, thought. Some of those stars are warming worlds right now. Some of those worlds may have conditions not entirely unlike Earth's. Each star is a local rebellion against the cosmic default, a temporary concentration of energy in a universe that trends toward dispersal and cold. The cold does not surround those stars the way darkness surrounds a campfire, with the fire holding its own against the night. The cold is not something the fires push against. The cold is the universe. It is everything. It is the vast emptiness of cosmic voids, the near vacuum of intergalactic space, the interstellar medium between the stars, the frozen darkness that will claim every stellar remnant and drift toward absolute zero across timescales. Beyond comprehension, the warmth of the stars and the rare, extraordinary warmth of the worlds around them is inscribed on that cold, the way a few bright sparks are inscribed on an infinite dark canvas. The sparks are real. Their light reaches across distances that should make them invisible and arrives at human eyes, enabling us to know that the universe exists and to ask questions about its nature. But the canvas dwarfs the sparks by every measure that matters: volume, duration, temperature. The ratio of cold to warm, of darkness to light, of emptiness to matter is not close. It is not even approximately balanced. It is overwhelmingly, definitively, permanently lopsided in favor of cold and dark and empty. We are the sparks asking about the canvas. The universe is cold, nearly all of it, nearly all of the time, and we briefly, improbably by the grace of physics and contingency and the patient accumulation of uncounted fortunate circumstances, are not. That exception is everything that has ever mattered, and it will not last forever, but it is here now, in this moment, warm against the cold, real against the emptiness, conscious against the silence. And that is worth every question we will ever ask about the dark surrounding it.